This project is on exploring the role of networks in predicting and improving social mobility. The motivation behind this is that the likelihood of becoming more successful than your parents is decreasing generation by generation. So it is more important than ever to understand these factors that contribute to social mobility so that we can make informed policy decisions as well as informed decisions to promote individual mobility. This was done using Facebook friend networks, income and mobility data. We developed networks to explore the relationship between social networks and social mobility. We looked at 3 key measures, and that is mobility, connectedness, and socioeconomic status, and developed a hypothesis that if a zip code is strongly connected to a zip code with a higher socioeconomic status, we expect it to have a greater likelihood of high intragenerational social mobility. And then in terms of network measurements, we determined that zip codes with high page rank should perform better at social mobility. On the right, you can see an example of a dark small node, which represents a node with high mobility but low median income in that zip code, compared to a light small node of a similar medium income but low social mobility. And you'll see that there is the higher mobility node is strongly connected to a higher income node, which is the larger node that it has the darker edge to.
So now we are trying to build a network. So in order to do that, we are going to use a data set from Facebook under the Data for Good platform of them. So the data which we're particularly interested in is how people are connected across locations. So in here, we are interested in their zip-wise connectivity data. And in order to calculate that, we use a very simple formula, which is which is a ratio between the number of actual Facebook connections divided by the total number of connections possible between any 2 locations I and J. So once we calculate that, we have social connected index, and it is actually scaled between 1 and 1 billion. And they are in linear scale. Say if the value increases from 1 to 2, it means that there is twice the amount of probability to have connection between the 2 nodes. So, and then in case of the New York, New Jersey state, which we picked, we had around like 1,923 edges, which is basically the zip codes. And then we had around 110 plus million edges initially. We just removed the social connected index, which are like too low, which is actually 1 in the case, and we just pruned those edges. And so this is what it actually looked like when we, visualized in Gephi. It doesn't make any sense, right? So that's when we decided that we need to do much more processing on the network. So we decided that to prove few more edges so that the edges don't dominate the view. And before we prune those edges, we wanted to make sure that we do all those calculations right. So we started with our one of the most critical values which we are going to focus on, which is economic connectedness. And how do we usually calculate is the number of high SES friends divided by total number of friends, and again divided by 0.5. That's how we usually calculate economic connectedness. But in our case, it's a little bit different since we are taking a higher level view. We are just viewing zip level instead of individual level. And to do that, we followed this technique of, calculating the sum of weights of edges across all high SES connected edges divided by the sum of all weights of all the edges. So here we know that the weights are actually the social connectedness index, which we got from the data. And so when we do this, we get the economic connectedness for each and every nodes. And we again calculate the median income for the set of zip codes which we are interested in. And from that, we define a particular zip code belongs to a high SCS category or a low socioeconomic status category. Basically, we compare the zips in mean income with the median mean income of the entire data set of zip codes we are interested in. And once we're done with that, we go with the mobility data, which is basically the average income percentile of, people born to parents who are in the 25th percentile of the national distribution income. And once we have that, we are calculating a mobility percentile. And once we have the mobility percentile, I think it's easier to interpret on it. So once this is done, we prune the edges and make the graph more visualizable, and this is how it looks. So here the high SES zip codes are in red color and the low SES zip codes are in green color. And we actually normalize the node size based on economic connectedness. So ideally, the larger nodes which are actually visible or have high EC value. And so this is how the graph actually looks like. You can go through, this is a video of it. So again, the red ones are high SCS zip codes and the green ones are the low SCS zip codes. And we can see that in general, high SCS zip codes are larger because they are more economically connected. And that's the nature of the graph. Yeah.
Yeah, so we started visualizing all the nodes and edges on a geographical plot, which was a plugin available from Gephi. So we did a lot of visualizations, which kind of made more sensical in this context. And the first visualization is plotting the nodes against the modularity score. So we ran the modulation algorithm on Gephi, and we found that the modularity score was 0.75. So this was a little surprising because we were dealing with a fully connected graph, and the only thing that differentiates the edges were the weights of the edges. So we did find a good amount of community structure, and we tried plotting different communities with different shades of green, and this is only the low SES nodes. And we found that the connectedness, the nodes which were together and which were exhibiting homophily were kind of clustered together and were part of the same community, and those nodes which actually exhibited homophily and were together were actually in the same size, which shows that highly economically connected nodes are together, and low economically connected nodes are in some way clustered together. And so the next hypothesis we did was actually testing what we are trying to say here. So highly economically connected nodes are exhibiting more amount of social mobility. So if you see in the graph, we are actually color coding the social mobility as a shade of green. So the lower social mobility nodes will be in lighter color, and higher ones will be high in color, which will correspond with high economic connectedness. So if you see in some parts of Manhattan and Brooklyn areas, we can see that larger nodes are a darker green, which kind of proves what hypothesis we are trying to prove here to an extent. So when we actually tried to, so this is the New York and New Jersey area, and this is the California's data. So Shandi will be talking more about this.
All right, so here we have California data on these two images. The node size is equivalent to its economic connectedness, and the node color is what is important here. So on the left side, we have graphed high SES and low SES nodes, and on the right, we colored the nodes by social mobility. You'll notice a pattern between high SES nodes and high social mobility. All right, and then we plotted the PageRank versus the mobility percentile. So the social mobility of the zip code versus the PageRank of the zip code. There is a slight upward trend, nothing significant to draw any major conclusions from. And finally, we plotted the clustering coefficient versus the mobility percentile as well. And this was done to support an idea in the social capital paper by Raj et al. Or Chetty et al., where they say that community leads to higher mobility, and we found similar evidence in that a higher clustering coefficient leads to higher mobility.
This is the plot we actually did for the PageRank versus the economic connectedness. So as you can see from the first graph, so we are color coding high SES nodes. So as we mentioned earlier, high SES nodes are basically zip codes who have a lot of rich people, and low SES zip codes are having zip codes with lower than the median income. So if we see here, the the bigger nodes correspond to a higher page rank, and we can see a lot of bigger nodes around this area where we don't have a huge cluster of nodes. So this kind of signifies how the PageRank algorithm works, because PageRank kind of distributes the influence of the nodes across the neighboring nodes. And we went ahead with the PageRank centrality to see how the nodes, how central the nodes were, because we understood that betweenness centrality and closeness centrality wouldn't work here, because these nodes are these networks are fully connected. And we couldn't also go ahead with eigenvector centrality because we are dealing with undirected edges here, because we are just talking about how connected two zip codes are. And the next graph here shows the connectedness of PageRank versus the mobility, which is kind of the result we are anticipating here. Okay, so the blue ones are high mobility, and the green and the red ones are low mobility. So if you see here, these are the high mobility areas, but you can see that the PageRank is very small because the nodes are pretty small here, and this is because these nodes are pretty clustered, and there are a lot of influential nodes across this particular cluster. So that there are a lot of high SES nodes which kind of play a huge influence in the mobility of across all the nodes here. So this is how we plotted the social mobility, how the social mobility works across different geographical areas with respect to connectedness. So the green areas in the entire graph signifies that social mobility is correlating with economic connectedness. So if you see here, around 50% of the map is colored green, which states that at least for 50% of the areas which we have chosen, the correlation between economic connectedness and social mobility works fine. And this plot is the like the correlation between the mobility percentile and the economic connectedness. So we did a similar plot for California as well. So we could see that the 50% hypothesis about the two factors being correlated together kind of fits in here. And in conclusion, we would like to point out that our research was only limited to the two major cities within the United States, while the paper which we followed had an analysis over the entire United States. So although we only got around 50% of the hypothesis proved, there is still room for future work where we can do the same analysis across different individuals instead of different zip codes, and with the better technical support. And we also found that the economic connectedness between high income states, where high income zip codes were more better than the low SES nodes. So
Yeah, so that's how we like to conclude. So one important point which we noted was high SES zip codes performed well in mobility compared to low SES zip codes, and which was quite in contrary to the initial hypothesis made by the paper Chetty et al., which said that low SES persons perform better in terms of mobility than high SES persons. But when we average it out and see it from the level of a zip code wise, high SES zip codes actually perform better in terms of mobility rate.